13.2 and then probably 13.3. And before you really dig too much into your notes, let's look here at this volume of prisms little diagram. So if we, hey guys, when you come in late, you normally try to not disturb class. We have something common between all of these. Whether you're doing volume of a rectangular prism, volume of a triangular prism, or volume of a circular prism, which we can actually call a cylinder, but it's still a prism since it clones the same shape on top and bottom. What is common between all of those formulas? All three of those formulas up there. Honestly, height is the common factor. So if I, with one color, highlight my height, so we've got height here, we've got height here, and we've got height here, then the other part that remains, here is my length width, here is 1/2 the base times the height, and here is pi times r times r. Which really then I can condense and make them a little bit easier. These are all the same formula. These are all just a manipulation of one single formula. Volume, now this only works for prisms. So remember, pyramids are going to behave differently. This is why we did prisms yesterday, and we're still on prisms today. Pyramids are going to behave differently, but volume of a prism, big B, what did big B represent? The base area times the height of the prism, or that's really the distance between the bases. And we will formalize that formula on our notes when we get there, but that is our general formula for volume of any prism. Once I know the area of the base, I can then multiply by the distance between the bases, and that will give me the volume.
So the volume is pretty much just the area of the base shape, and then multiply by how long it is?
Yep, distance between your bases. Okay. So sometimes people use L for how long is the shape. Sometimes they use H, sometimes they use D for distance between bases. I don't care what you use as long as you remember what you're doing. It's that base shape area times the distance between. Because if you think about it, like taking 2 dimensions and making it 3 dimensions. So if we have a 1 inch by 1 inch by 1 inch cube, let's imagine that this little cube on the corner is a 1 by 1 by 1. We'll just call them 1 units. So if I think in 2 dimensions, then I could just have a 1 by 1, like a square. And I could have, like we talked about yesterday, 9 of those squares if I had a 3 by 3. Now obviously here we'll have 2 by 2, but just stick with me with the imagining. What's up?
Do you have one of the graphing calculators?
No, Mr. Hall has all of them.
Okay.
Did he send you in here?
Yeah.
Tell him he's crazy. I have none of them. He has. Now hold on. Do you want to borrow my personal one? Are you out of calculators?
I think so.
If you guys ran out of calculators, that's different. Here's the fancy pants one, but my personal one's at home because my wife needed it.
Thanks.
You're welcome. Hey, make sure I get that back. Yeah. So, if we had the base area of 9, and then stacked up, well, I have a 1 9 on the bottom, another 9 in the middle, and another 9 on the top. That's why we do that base area times how many layers, or what's the distance between. So when you think about that distance, we're really kind of talking about layers. So let's think about misadventure again. So misadventure, which is a play on words, by the way, because a misadventure would be like a bad adventure. So misadventure, talking about the person. She buys 1 inch by 1 inch by 1 inch wax cubes. These are actually kind of real things called sensies. And she then has a box that is 2 inches by 2 inches by 2 inches. So I want you to figure out how many cubes could she place into this box versus how many cubes could she place into this box. Now we could do it mathematically. Try to draw this. If you're able to draw in the 3 dimensions. So try to do it on your own, but if you're totally stuck, you can look up here. But we know the dimensions of our wax cube, or the candle as they say, is 1 by 1 by 1.
Are we ever going to use the graphing calculators this year?
Probably not this year. Sorry, I have a glitch spot right here, as you can see. Yeah, so it kind of looks like we wrapped this box up with a ribbon. Because I now made this 1 inch by 1 inch by a 1 inch depth. So if I made those dotted lines, we'd have those dotted lines back there that we cannot see. Yeah, so it's kind of, but, so I could fit how many cubes on the bottom layer of the box? Anish? 4, right? Because I'm 2 wide and 2 deep. These are notes from yesterday, dude. I gave you them stapled together. Were you here yesterday? Right here. Right, in accelerated 7. The 13.1. We're on 13.2, but I didn't put it yesterday. So there's 4 on the bottom. Then, Nish, how many layers am I going to have?
So there's 4 on the bottom, so they'll have to be 4 on the top.
Yeah, so I'm going to have 4 times 2 layers, and we end up fitting 8 candles here, or we could say that's 8 inches cubed. Now we can do the same thing with my larger box over here. It's 4 by 1 by 2. So if I drew that here, we'd be going across, then back to back, and then I could split in the middle, and I could split again here, and split again there, and look at the bottom layer, and Andrew, I could say on the bottom layer I'm going to be able to fit, 4 again, and then how many layers? 2, so again, we get 4 times 2, or 8 inches cubed. What this is trying to reinforce, sorry, I'm trying to move that cursor somewhere else so it gets off there. What this is trying to reinforce is that you do not have to have the same dimensions in order to get the same volume. Because think about it. 2 times 2 times 2 equals 8. 4 times 1 times 2 equals 8. So there was a problem from your homework that was kind of a challenge where it gave you the area of the faces, and you had to work backwards to then find volume. And I put that on there because I knew that most of you guys know volume of prisms from 6th grade using a different formula. So we talked about big B times H. But when you guys talked about this in 6th grade, you probably had a different formula that you talked about that was pretty simple. Length times width times height. Now, the only reason we don't use that now, this height, well, height of what? Is that height of the base, height of the prism, height of the... And what then if I have a triangular prism? Length times width times... Crap.
Height times half.
So this is why we use a different formula. This doesn't always work. So like what we talked about on that start slide, this height we got to talk about as distance between the bases, and this length times width we actually have to talk about in any situation being that base area. So instead, we really kind of get rid of this formula. It used to work, and it still can work, but we have a better one. Our better formula is big B times H. Label that this is base area, and this is distance between bases.
Isn't that pretty much just the same thing?
It is the same thing if it's a rectangular prism. If it was a triangular prism or a pentagonal prism or a hexagonal prism, the area of this base is not length times width.
Yeah.
So that totally changes. This works for any prism. This only works for rectangular. Any questions? So we're going to move a little quickly through this. So, how do you think it'd be different in a cube? So let's think about that length times width times height. Well, if I have a cube and I set up that the volume is length times width times height, well, that would still work because it's still a rectangular prism. But here, my length, width, and height, because it's a cube.
That works.
I know it works, but how could we make this easier? How could we make a simpler formula? Because it's a cube, what relationship can you say between the length, the width, and the height? Sean? So this I could replace with whatever the edge length is. This I could replace with the edge length. And this I could replace with the edge length. So I can really make that formula the edge length cubed. Now that only works for cubes, but it works out really, really nice. So when we come down here and we start looking at these examples, by the way, I'm fairly certain these are the exact same shapes from our surface area examples. So if you are interested in comparing surface area and volume.
They are. They're the same question.
So again, start by finding that base area, which actually, if you look at yesterday's notes, we already know these base areas. So if I call this 9 by 2 face my base, my big B becomes 18. Then to find my volume, I'm going to take that big B and multiply it by the height between the bases. Now check this out. I used the 9. I used the 2. The only thing I haven't used is the 3. I got to use it. When we're doing volume, we never leave a number, well, unless they give us too many numbers. So wait until we get to more complicated shapes and they might give us too many numbers. But in situations like this, we got to use every dimension. So this becomes 18 times 3, and my volume is actually 54 feet. Volume is cubed.
We already got this in the next one. If you actually calculate it, we already have it.
Ah, so Andrew's recognizing
It's a cube.
that cube, this cube, 3 by 3 by 3. Guys, that's a Rubik's Cube, essentially. So if you've got 3 by 3 on the bottom, then stacked 3 tall, we can just set up, what color am I on? Should probably change colors. We can just set up the edge length cubed, which is going to be 3 cubed, which is 3 times itself times itself. So 3 times 3 gives me 9, and 9 times 3 gives me 27 feet cubed. There's a couple different algorithms. I learned based off Grace's YouTube channel, actually. She has Rubik's Cube algorithms as one of her videos. Now, when we have rectangular prisms, make your life easy. Because I can set my rectangular prism like this, and the bottom is my base. I can set it like this, and the bottom could still be my base. I could set it like this, and the bottom could still be my base. Because it's a rectangular prism. Every face is a rectangle. So, you can actually make whichever face you want be the base, and then the leftover dimension is your height. So here, still the 3 times 2 is real easy to do, so we can leave that as our base. So our base area, 3 times 2, is going to give me 6. So then to find that volume, we set up 6 times the 4.2, the height that we have not used yet.
20. No.
Yeah, 24 plus another.
25.2.
Yeah, 25.2. Because 6 times 4, then 6 times the 0.2. And this still is feet cubed. Guys, if you don't have labels, it's wrong. Like, really, if you don't have labels, it's wrong because we don't know if you're talking about feet or feet squared or feet cubed or dogs, cats, pizzas, bananas. We don't know. You gotta have labels.
Well, I mean, I don't think it could be a dog. It's 25.2 feet of a dog.
I mean, you can chop them
Maybe there was an accident.
Like more than a whole dog.
Or less than a whole.
Maybe it's a Siamese twin dog.
And our final one here. What's the area of the base? 6 times 9 gives me 54 feet cubed. Again, notice two different sized rectangular prisms have the same volume inside. So this brings up the question, and we'll dig deep into this here coming up shortly. Which would be cheaper? You ever think about why companies package things the way they do? Like, Sean, you ever think about why that Muscle Mop comes in a carton as opposed to potentially a can or a bottle or anything else? Everything comes down to price, right?
Yeah.
So somehow that container, which is really, what kind of shape do you have at the bottom? Is that like a square at the bottom? Yeah, so that's like a square-based prism up until the fact that the top is like pinched and then folded. But the volume they can fit in that shape, there's a reason. There's a mathematical and a cost-effective reason why they made that choice. So now, what if my edge length is less than 1? So my cube, my formula would still be edge length cubed, but my edge length here is 3/4. So if I cube a fraction, this is 3/4. So if I say volume is edge length cubed, but the edge length is 3/4, so that becomes 3/4 cubed, which really becomes 3/4 times 3/4 times 3/4. So when you take a fraction to a power, all we actually do is take the numerator to the power and the denominator to the power. 3 to the third power, we already talked about it. 27. 4 to the third power, 4 times 4. 16, then times 4 gives me 64. Is this reducible? 3/4?
Wait, no, it's not.
Pretty sure 27 is less than half of 64. It's not reducible. I'm just curious to see, what is it as a fraction? Or sorry, what is it as a decimal?
It's 2.370 repeating.
It is not 2.37. You did your division upside down.
Oh, I did. Okay.
So wait, what? Hold on. 3/4 is 0.75. But yet when I look at the volume, I got a smaller number. How did I get less volume than my edge? Julian?
Wait, what?
Okay, but why then do I have less? I agree, fraction multiplication makes smaller numbers, but I'm trying to rationalize, like, how does this make sense? If you think about, like, a 1/2 inch, I mean, so 3/4 is a little bit weird to work with. Think about a 1/2 foot. 1/2 foot by 1/2 foot by 1/2 foot. Well, how else could I talk about 1/2 foot? Awesome. How many inches?
I don't know how many inches are in a foot.
Yeah, 6 would be 1/2 foot, right? So I could do 6 times 6 times 6. And then my answer would get bigger, right? Because 6 times 6 times 6, that's going to give me a bigger answer. Here's what I'm trying to make you realize. And I like that a lot of us are sitting here just like trying to process it and not talking to our neighbors or anything like that. This is feet. What label is this?
Inches.
Feet
That's also
Cubed.
cubed.
What?
These are not the same value of numbers.
How'd they change?
Feet, because this was feet times feet times feet. This is your volume, dude.
Oh, okay.
This is the length of the edge. This is the volume in it. Do not let your brain play tricks on you. This is not smaller because it's not comparable. You cannot compare feet with feet cubed. That's like comparing length to mass. You can't do, like, they're not the same thing. This is how much space is inside of the object. That is how far is it from corner to corner? They're not the same types of numbers. Do not try and compare them. This is where people get confused, and they're like, there's no way that's true. It doesn't get smaller. My answer gets bigger. They're not the same type of numbers. So just make sure you understand that the unit is what tells me what type of number it is and lets me understand what can I actually compare it to. If you wanted this to be easier, use inches so that you can avoid fractions, because then we could just do 9 times 9 times 9, 3/4 of a foot, 9 inches, and then we get a whole number answer and it'd make more sense. Right?
Found these notes on the ground. They don't have a name.
Okay, put them in the lost and found.
Okay.
Thanks. Flip to the back. We gotta move quick. I'm gonna try to get to the next one. So now we have a really interesting problem, and I like these sort of problems. There's a couple like this on your homework. The cube has a surface area of x square units and a volume of x square units. Or, sorry, x cubic units. These are not equal. This is x square units. This is x cubic units. They're using the same number. So say they're both 16 or they're both 50 or they're both 100, whatever, but they're not equal really because volume and surface area are not the same type of values. Is anyone confused at what I'm really trying to say? Square units is how much flat space, cubic units is how much total three-dimensional space. Honestly.
So here, x and x are the same thing.
They're the same number.
They're the same number, but they're not the same unit.
They're not the same value because their units are not the same. One is like representing this piece of paper. It's flat, it has space, right? It covers area. If I put it on me, it covers area. The other is representing volume. I have an amount of water in here. I cannot talk about these square inches of water that I have. That would not really make sense. I talk about cubic liters or milliliters or ounces, or those are all cubic measurements. So, what's the edge length of the cube? Well, we know the edge length is less than 10. So, okay, if they're the same number, then mathematically they're the same. Now, we're not saying they actually represent the same thing, but we could set them equal. So, I know the surface area is equal to the volume. In a cube, how did we say we found surface area? And you can flip back to your notes if you need, Anish.
Lateral area times base. Plus.
Cube was real easy, actually.
Cube is 6 times s squared.
So this, my surface area, will actually be represented by 6 times s squared. Or actually, I like e squared better for edge length. Side is just a word that's kind of dangerous.
Why?
Because side is not really specific to whether you're talking 2-dimension or 3-dimension or 1-dimension, like length, width, or length and width. Or edge is speaking specifically the edge between two faces. Side could mean side or side. Because this is a side of the square. This is a side of the cube. So that's why side is a dangerous word to use. This is an edge. This is a face. Those are the more specific words we want to use. So then when we talk about the volume, well, how did we find volume? We just did it. It's the edge cubed. So wait, we said that when we square something, it's that times itself. And when we cube it, it's itself times itself times itself. So if I start to get rid of what I can get rid of, that is the same on both sides. Lana, so what could I do on both sides?
On both sides, you could divide by e twice.
Yeah, so I could divide by e times e, or I just divide by e squared.
And then you'll have 6 equals e.
So if I divide by e, and I divide by e times e, these cancel, these cancel, these cancel, these cancel, and we end up seeing that e, the edge length of this cube, must be 6, and if you test it, that'll work. If this is 6 whatever, centimeters, inches, millimeters, doesn't matter, numerically, the numbers for surface area and volume will come out equal. That doesn't mean they're actually the same. They just come out to be the same number.
So we have a cube that has an edge length of less than 10, and the cube has a surface area of x square units of x.
So actually, we can work backwards now and find the surface area. So with this, so hang on, because I realized we should do that. So hang on to your question. If I do 6 squared, that's 36. 36 times 6 gives me that the surface area here. What's 36 times 6? It'd be 180 plus another 36. We get 216, I believe. So that's 216, let's say, inches squared. And the volume would also be 216, but it's inches cubed. So they come out numerically the same, but mathematically they are not representing the same thing. One is square units, one is cube units. So go ahead.
What's that formula right there, though? What's that represent?
Which one?
The edge length? Oh, the one on the right. That's the
That's volume. So this is surface area, and this is volume.
Oh, okay.
Her volume is just the edge length cube.
Oh, and to the
Yeah.
left
Is
is
there
right.
any number other than 6 with which this would?
Ooh. That I'm going to leave as a question for you to ponder. Are there any, like, potentially what if we went bigger than 10 or something like that? That I will tell you is the easiest one to solve. But I'm going to leave that as a challenge for you to figure out. Will that ever, are there any other numerical edge lengths that would let this
I
happen?
think there shouldn't be, because the only reason we got 6 as the answer to that is because it's
The
right.
algebraic process. It's a good hypothesis. Volume here! We got to touch on these, and then we are going to go to pyramid work. When we look at a triangular prism, it told me what the base is in its name. So now to find my big B, remember in a triangle, our formula is different. By the way, I threw some formulas right here and some formulas right over there. If you forget things and you need to remember area formulas or anything like that, area of a triangle is 1/2 little b times little h. And the little b and the little h are always perpendicular. So look for that right angle. That tells me that my little b and little h are 12 and 5.
Wait, how do you know the height is 5?
That's the height of the triangle. So we talked yesterday about in a triangle, any triangle, regardless of how it's made, the height has to be perpendicular to the base.
It's a right angle.
So base height, wherever the right angle is, that tells me that that's the base and that's the height. Here we have a right triangle. So the base and the height are the two legs. The other side would be our hypotenuse, but we don't care about that because all we care about is the base and the height. We don't need any other measures. Well, for the triangle. We then, and this is where it's dangerous, we have two different heights. That's why we use little h for the triangle height, and for the prism height, we'll use big H. So this, my big B, comes out to be 30. I then define the volume, do my big B times big H. So that comes out to be 30 times 17. Get 500,
Oh.
510.
Yeah.
And we do not have any label,
It's cubed.
so we gotta use units cubed. We have to have a label on it. Even if they didn't label their values, we use the assumptive units. Because then once we're told the units, we would just plug it in. Try the got it on your own to check if you are able to do this. If you wanted to write the formula all out together, you could. You do 1/2 little b times little h times big H if you felt like doing it all together. your calculator. You can do this all at once, but I still advise that you write this out to check, did I use every dimension that was given to me? I used the 4, that was part of the triangle, and the 3.5, that was part of the triangle. Then the 11.6 is the distance between my two triangle bases. When we compute this all, initially see with the calculator, you got it?
Yeah, 81.2 meters squared.
You verified, Jeremiah?
It's good. I verified.
Said 81.2. And they did give us a label now, so we use meters cubed because we're talking about volume. Any questions on this stuff? And I realize that we might not be able to, actually, we will not be getting to 13.3 because hexagons. So, hexagons. If I have a hexagon, Jeremiah already blurted this out, but what do I really have if I want to start to think about my shape in more simplistic terms? Colin?
6 triangles.
I have 6 triangles, so go ahead and separate this out into your 6 triangles.
We never did like this problem for the surface area.
I know, so that's fine. The surface area would not, we'll use this same information if you wanted the surface area. All you would then have to do is still apply the perimeter times the height for that lateral area. So this hexagon is really 6 triangles. So I'm going to say 6 times the triangle area. So my hexagon area, let's say area, or actually big B, because we know that's the area of the base, so we can just say big B is going to equal 6 times my triangle area formula. Now my triangle area formula is half the little b and little h. You gotta remember, little b and little h have to be perpendicular. They have to make a right angle.
Oh, okay.
So, my little b is the edge of the triangle here, which I'm told up here is 3, and the height over here I'm told is 2.6. And little b comes out to be, well, half of either of these is kind of, well, I could do half of 2.6. So I can do the half of 2.6 gives me 1.3 times 3, it gives me 3.9, then times 6, anyone got it? 23.4, okay, I thought you said 0.5, sorry. And that's inches squared right now because that's our base area. So we just calculated this area. That's a weird color when drawing on top of that. It's like teal. Now to find volume, we just got to take that value times the 4 because that's how tall or the distance between the hexagons. So that comes out to be, it's a little under 100.
94.
93.4.
Nearest to nearest.
To the nearest cubic inch. So round either up or down, whatever you need to do.
99. It's 93.6.
Well then where would it round, up or down?
I do it. I meant to say.
It is okay. So try, I'm going to give you a few minutes, like 2 or 3. Try this one. We first have to break up our big B into triangles, calculate that big B, then we'll find the volume. If you're stuck, feel free to work with neighbors or stick up a hand if you're really stuck and I can come by and help you. And by the way, guys, this technique will work with any regular polygon. What does it mean for a polygon to be regular? Like a square is a regular polygon. An equilateral triangle is a regular polygon.
It has equal sides.
The edges have to be equal. So regular polygons have equal edges. So all these shapes up here are regular shapes. This is a regular pentagon. All 5 sides are the same. By the way, if you want a shortcut, now shortcuts are oftentimes dangerous. You go through those dark woods, you might meet a wolf. I could immediately, if you felt like it, combine the 6 and the half, and I could just make my formula 3 times little b times little h. I caution you not to do that. Because I saw people like, oh, I could just do this always. But guys, what about when this changes to an octagon, or a decagon, or a nonagon, or any of those other polygons? This is how many edges are on your polygon. So this is going to change as your polygon changes. So I caution you, keep that how it is and preserve your triangle formula so that we then just have our half. Now what are the base and height for my triangle? You know?
Yeah, the base height is 5.2, so 6.
Well, yeah, 6 and 5.2. So Moon, what'd you get for your big B?
For the big B, well, I didn't.
So you didn't calculate your base area
No,
first?
I didn't.
Well, so you did it right. You'll get the same thing even if you took a slightly different method. So what'd you get?
I got
Verify?
1,020.
So let's check it. Half of this 6 is 3 times 5.2 would be 15.6 times 6.
It's 93.6. Yeah, 94. If you round it.
At the end. You round at the end once you get your volume.
And
Then, to find the volume here,
you multiply it by 10.9.
the distance between that we haven't used yet.
And then that's 1,020.24.
The rounded.
Yeah.
What is it?
It's 10,020 if you round.
10,000 or
I
1,000?
mean, 1,020 if you round.
So, 1020?
Yes.
Okay. Label?
Centimeters cubed.
Centimeters cubed. Alright, I have a question. Hold on, I have a couple minutes. So, I was debating what, obviously we're doing something fun tomorrow, like review game, whatever, but I was debating on how we really want to do this. Would we, like we've done before, want to do the review game where we like do Jenga and the questions and like teams and answer? Or, hold on, or I have an activity that can be adapted depending on the chapter, dealing with geometry, where you would go around the school and with your phones, or well, really now that most everybody has phones, you do small groups, and you would be searching for the things that we learned last chapter in real application around the school. So talking about two-dimensional cross-sections of three-dimensional shapes. So what I would be asking you to do is go find three-dimensional shapes and then talk about what two-dimensional cross-sections you would find depending on what cuts you would make. So here's really the question. Do you feel like you need more practice and more review to actually be comfortable for the test, or would you like to just do an activity to explore and go a bit deeper in this learning? So shut your eyes If you just want to review games, sit here in the classroom, solve problems, play Jenga, stick up your hand. That is option 1. If you feel comfortable on that material and you'd rather go deeper and have an exploratory activity, and then like we would bring it back and share with our classmates, stick up your hand for that option. All right, put your hands down. Overwhelmingly, option 2 wins. So I will adapt that activity tonight and plan on that being what we do tomorrow. You're still like a minute ahead, so please be quiet in the hallways. Do not distract your peers in their classes.